6.9 Periodic Table. We fill orbitals in increasing order of energy. Different blocks on the periodic table, shaded in different colors in this chart, correspond to different types of orbitals. We can see that the s orbitals are represented in blue, the p orbitals are represented in pink, the d orbitals are represented in orange, and the f orbitals are represented in the beige color. We know that there's one s orbital that holds 2 electrons. There are 3 p orbitals, which will hold a total of 6 electrons. There are 5 d orbitals, which will hold a total of 10 electrons. And there are 7 f orbitals, which will hold a total of 14 electrons. There are some anomalies in the periodic table. Some irregularities occur when there are enough electrons to half fill the s and d orbitals on a given row. For instance, the electron configuration for copper is argon 4s1 3d5 rather than the expected argon 4s2 3d4. This is because it is 1 electron short of having a half-filled d subshell. And there's a rule that says that half-filled and completely filled subshells are most stable. So it borrows 1 from the 4s and puts it in the 3d, and now we have both the 4s and the 3d subshells being half-filled and more stable. This occurs because the 4s and 3d orbitals are very close in energy, and these anomalies occur in the f block atoms as well. Sample exercise 6.8, electron configurations for a group. What is the characteristic valence electron configuration of the group 7a elements, the halogens? First, we locate the halogens on the periodic table and write the electron configurations for the first 2 elements, and then determine the general similarity between them. The first member of the halogen group is fluorine, atomic number 9. The condensed electron configuration for fluorine is helium 2s2 2p5. Similarly, that for chlorine, the second halogen, is neon 3s2 3p5. From these 2 examples, we see that the characteristic valence electron configuration of a halogen is ns2 and p5, where n ranges from 2 in the case of fluorine to 6 in the case of acetine. This also tells us that the halogens have 7 valence electrons. Practice exercise. Which family of elements is characterized by an ns2 and p2 electron configuration in the outermost occupied shell? Practice writing those electron configurations. Sample exercise 6.9, electron configurations from the periodic table. Write the electron configuration for bismuth, element number 83. Write the condensed electron configuration for this element. How many unpaired electrons does each atom of bismuth possess? We write the electron configuration by moving across the periodic table 1 row at a time and writing the occupancies of the orbital corresponding to each row. So in the first row, which includes hydrogen and helium, the electron configuration starts out as 1s2. In the second row, we start out with lithium, and our configuration across the second period would be 2s2 2p6. The third period would be 3s2 3p6. The fourth period, 4s2 3d10 4p6. The fifth period, 5s2 4d10 5p6. The sixth period, 6s2 4f14 5d10 6p3. And we can total these up for the entire electron configuration. Note that 3 is the lowest possible value that n may have for a d orbital, and that 4 is the lowest possible value of n for an f orbital. So we do not have any d orbitals in the second shell or the first shell. We do not have any f orbitals in the first shell or the second shell or the third shell. So just keep that in mind when you're writing your electron configurations. The total of the superscripted numbers, if I were to add up all of these superscripts, should equal the atomic number of bismuth, which is 83. The electrons may be listed as shown above in the total row in the order of increasing principal quantum number. However, it is equally correct to list the orbitals in the order in which they are read from the periodic table. We write the condensed electron configuration by locating bismuth on the periodic table and then moving backward to the nearest noble gas, which is xenon, element number 54. Thus, the noble gas core is Xe. The outer electrons are then read from the periodic table as before. Moving from Xe to Cs, number 55, we find ourselves in the 6th row. Moving across this row to get to bismuth gives us the outer electrons. Thus, the abbreviated electron configuration is xenon 6s2, 4f14, 5d10, 6p3. Or if you want to put it in order of increasing principal quantum number, you can list it this way. We can see from the abbreviated electron configuration that the only partially occupied subshell is the 6p. The orbital diagram representation for this subshell would look like this. In accordance with Hund's rule, the 3 6p electrons occupy the 3 6p orbitals singly with their spins parallel. Thus, there are 3 unpaired electrons in each bismuth atom. Practice exercise. Use the periodic table to write the condensed electron configurations for cobalt and tellurium.